viewers, my name is Zanele Saleni from Ebenezer Madomboze High School. Welcome to ECDOE Broadcast Studio. Today's lesson is about the overview of Paper 2. So we are recapping from what we have done, which we have covered some of the topics in Paper 2. Your question 1, multiple choice question. Question 2, organic molecules. Question 3, organic properties. Question 4, we looked at organic reactions. Question 5, we looked at rates of reaction. For today's lesson, we are going to go straight to chemical equilibrium. Let's get to chemical equilibrium. One, when you talk about chemical equilibrium, you need to be able to understand open system. What is meant by open system? What is meant by a closed system? What is a reversible reaction? What is meant by chemical equilibrium? Now, if you know those concepts, then you will have a better understanding of chemical equilibrium. One, we have said in class as teachers that your reaction will never get to a point whereby it reaches a chemical equilibrium. One, unless the reaction is a reversible reaction. Two, the system must be a closed system. Now, we will then, like we did in rates of reaction, look at the factors that influences the equilibrium position. Factor number 1 that we will look at is pressure. Pressure is always associated with gases only. We look at concentration, and lastly, we look at temperature. Now, when we are unpacking all of these factors that influence the position of equilibrium, we are looking at the principle which is known as Le Chatelet's principle. It states that when an equilibrium in a closed system is disturbed, the system will reinstate a new equilibrium by favoring the reaction that will oppose the disturbance. Now, when you look at this question, you should know at all times that you always need to be able to identify the disturbance. Now, you are always going to be asked to explain what will happen to the equilibrium in terms of Le Chatelet's principle. Number 1, you need to identify the disturbance. 2, we know what Le Chatelet's principle says. It talks about the system favoring the reaction that oppose the disturbance. Now, you are not going to talk in Ngangala language when a vague, because now you know you have identified the disturbance. Now, if the disturbance is an increase in temperature, when you talk in step number 2, you will talk about the system favoring a reaction that will decrease the temperature, because the disturbance was an increase in temperature. So what opposes an increase in temperature is a decrease in temperature. Number 3, you state how will that be managed? What will be favored? Now you need to know, if you talk about temperature, we talked about 2 types of reaction. We talked about exothermic reaction. We talked about an endothermic reaction. And when you are defining them in rates of reaction, you have said your endothermic reaction is a reaction that absorbs heat from the surroundings. You talked about your exothermic reaction as a reaction that gives out heat to the surroundings. When exothermic reaction is giving out heat to the surroundings, it simply means temperature is increasing. If your endothermic reaction is absorbing heat from the surroundings, it simply means temperature in the surroundings is decreasing. Now, when you talk about this, you need to have that understanding. Now, point number 4, you state which reaction will be favored. Now, remember, we have got 2 types of reactions, because now we are talking of reversible reactions. When you talk about reversible reactions, it simply means you have got a forward reaction and you have got the reverse reaction. Whenever an endothermic reaction is the forward, your exothermic will be the reverse. If the forward reaction is exo, the reverse will be endo. Now, if you talk in terms of concentration, whenever you are increasing concentration of reactants, you will favor the reaction that uses up those reactants, which becomes the forward reaction. If you are decreasing concentration of reactants, you will favor the reaction that increases concentration of reactants, and that becomes the reverse reaction. If you talk in terms of concentration of your products, whenever you are decreasing concentration of products, you will always favor the reaction that increases concentration of products, and that becomes the forward reaction. And if you are increasing concentration of products, you will always favor the reaction that decreases concentration of products, and that becomes the reverse reaction. And the last concept that we talk of is a change in pressure. So whenever pressure is increased, the system will always favor the reaction that decreases pressure. Now, the reaction that decreases pressure, you look in terms of gases. It is the reaction that produces few moles of gas. If you talk about a decrease in pressure, we know that the system will favor the reaction that increases pressure. And the reaction that increases pressure is a reaction that produces more moles of gas. So you will be looking at a balanced equation, but you are only focusing on gases when you talk about your factor being a pressure. And number 3, you need to state, your number 5, you need to state the effect on the number of moles of your product or of your reactants. And in most cases, they don't ask it in terms of moles of your products or reactants. They'll ask in terms of yield of products or yield of your reactants. Now, part 2 of the chemical equilibrium, it is the equilibrium constant. Now, you need to remember, when you are writing an equilibrium constant, you will be given a balanced equation. Your Kc is equilibrium constant, which is denoted as UKC. You look at your equilibrium constant being the concentration of your products divided by concentration of your reactants. Now, if you write Kc expression as concentration of product divided by concentration of reactants, you don't get a mark. Now, you need to look at your reaction. For example, if you look at a reaction, your reaction, your hydrogen reacting with your nitrogen, you get as a product your ammonia. That reaction will always be given to you balanced. Now, if you were to write Kc, you don't talk about your Kc being concentration of products over concentration of reactants. You know what is your product. Your product is ammonia. So it's going to be concentration of ammonia. The balancing number becomes the exponent, which is to the power of 2. Divide by, there are 2 concentration of reactants. So there's concentration of hydrogen. Balancing number on hydrogen, which is 3, becomes an exponent. Multiply, not plus, concentration of nitrogen. Now the balancing number in nitrogen is 1. So anything to the power of 1. So this becomes your Kc expression. If you were to write it as Kc being concentration of products over concentration of reactants, that is not an expression. Now you need to also remember that your chemical equilibrium does not have unit, because you look at the ratio between concentration of your products and your concentration of your reactants. Now you need to compare Kc values. For your larger Kc value, it means concentration of products was higher than that of reactants. If your Kc is small, it simply means concentration of product was smaller than that of your reactants. And if Kc is equal to 1, it simply means there was an equal amount of concentration of your reactants and of your products. And we look at calculations that would involve your mole ratio, where you are calculating that equilibrium constant. I usually say to my learners, they should do away from having the table method. Instead, they should make use of the mole ratio. But what is important is on you arriving at the answer, the how part of it, do the way you know how. Let's get to the second topic for today, which is acids and bases. There are 2 theories that I used to define acids and bases. We make use of Arrhenius theory and we make use of Ulrich-Bronsted theory. You should be able to define acid and a base using both theories. Now remember, When we talk about Bronsted, we talk about your acid being a proton donor and your base being a proton acceptor. But when you talk about Arrhenius, we talk about an acid as a substance that produces your hydronium ion in water, and a base as a substance that produces your hydroxide ions in water. Now, when we talk about production of your hydronium and your hydroxide, remember in grade 11, we talked about your conjugate acid-base pair. Now, if you were to look at your base, your ammonia reacting with water, your ammonia is accepting a proton. Your water is donating a proton. So it simply means your ammonia is a base. Your water in this instance, it is an acid. When a base has accepted a proton, it becomes a conjugate acid. When an acid has donated a proton, it becomes a conjugate base. Now, when you look at conjugate acid-base pair for that reaction, you would have your ammonia and your ammonium ion, NH4 plus, would be your conjugate acid-base pair. Or you look at your conjugate acid-base pair as your water and your hydroxide ion. Now remember, when we talk about a conjugate acid-base pair, we talk about a pair. So this question will always be there. The 2 marks that will always be there. You need to be able to identify a conjugate acid-base pair. You look at reaction number 2, you have got an acid, which is your hydrochloric acid reacting with water. And you get your hydronium ions and your chlorine ions. Now in this instance, your water is a base, your hydrochloric acid is an acid. Now when an acid has donated a proton, it becomes a conjugate acid, a conjugate base. When a base has accepted a proton, it becomes a conjugate acid. Now your conjugate acid base pair would be your H2O and your H3O plus. And you look at another conjugate acid base pair for reaction number 2, it is your HCl and your Cl minus. Now if you were to take notice, your water in reaction number 1 is an acid, while your water in reaction number 2, it is a base. There are substances that are said to be amphoprotic acids. Your amphoprotic, I mean amphoprotic substances. A substance that can act as either a base or an acid. That substance is known to be an ampholyte. Now, when you have got your acids and bases, you need to look at the strength of an acid and the strength of a base. There are acids and bases that are said to be strong. There are acids and bases that are said to be weak. You need to be able to differentiate a strong acid from a weak acid, a strong base from a weak base. Now, by differentiating the two, you need to know when we are defining a strong acid, we talk about a solution of high concentration hydronium ions in a strong acid and a low concentration of hydronium ions in a weak acid. Now you need to be able to compare the Ka values. That if you look at Ka value of a strong acid, it would be greater than 1, and Ka value of a weak acid, it would be less than 1. And there are 4 acids that we look at as our strong acid. It is your hydrochloric acid, your sulfuric acid, your nitric acid, and your hydrobromic acid. You look at different acids that are your weak acids, which is your ethanoic acid, your oxalic acid, your hydrofluoric acid, your phosphoric acid. Now, differentiating the two, you can differentiate them in terms of Ka value, or you can differentiate them in terms of the definition from examination guideline that the other one ionizes completely in solution to form high concentration of hydronium ion, while the other one ionizes completely in solution to form low concentration of hydronium ions. Look at a strong base and a weak base. A base dissociates in water. Now, your strong base would dissociate in water completely to produce high concentration, of your hydroxide ions, and you look at a weak base, your weak base dissociates incompletely to produce low concentration of your hydroxide ions. So you can also differentiate a strong base from a weak base by comparing the Kb value. When there is a high Kb value, it simply means that base is a strong base. If there is a low Kb value, it simply means that base was a weak base. Now, there are acid-base reactions that we look at. Whenever you are reacting an acid and a base, we always say that reaction is neutralization reaction. And what we want to achieve in that, we want to get a neutral substance. But as you are reacting your acid and base, what we usually get is salt and your water. How will it be? It depends on the type of acid and the type of a base that has been used. I usually say to my learners, during acid-base reaction, we make use of indicators. Now, before you are able to choose an indicator, you need to know this, that if you are reacting a strong acid and a strong base, the solution will be neutral. If you are reacting a strong acid and a weak base, the solution will be more acidic. If you are reacting a strong base and a weak acid, the solution is going to be more basic. Now, in order for you to choose best indicator for each reaction, you need to look at a pH range. For a solution that is going to be more acidic, it simply means we are using methyl orange. And for a solution that will be more neutral, we are using promethanol blue. For your solution that is going to be more basic, we are using ephenolphthalein. Now, you choose your indicators based on the type of acid and the type of base that has been used. And during your acid-base reactions, also to test how the solution will be, we make use of salt hydrolysis. Now remember, I have said to you, when you are reacting an acid and a base, you will get a solution, but that solution is a solution where you have got your salt and your water. Now, I have said that if it's a strong base and a weak base, pH will be less than 7 because it's going to be acidic. If it is a weak base and a strong, if it's a weak acid and a strong base, that is going to be basic, which is greater than 7. A strong acid and a strong base, that pH will be equal to 7. Now remember, if pH is equal to 7, that salt will not undergo salt hydrolysis, because when you have got a strong acid completely ionizes in water. When you have got a strong base, your strong base completely dissociates in water. Now you have got equal ratio of your hydronium ion and your hydroxide ions. So hence it is going to be a neutral salt. Now when your substance is undergoing salt hydrolysis, one, you need to have two ions, a positive ion and a negative ion from the salt. You need to have a positive ion and a negative ion from the salt. You need to determine the base from the positive ions, and obviously the acid will always come from the negative ion. You need to be able to determine which acid was there and which base was there. Both acid and base are identified by if they are strong or weak. If it is strong, it does not undergo salt hydrolysis, but for your weak ones, they undergo salt hydrolysis. Now, when you take a substance and you make it undergo salt hydrolysis, remember, salt hydrolysis, you are just reacting salt with water. When that salt is undergoing salt hydrolysis, if it produces your hydroxide ions, it simply means that salt was basic. If it produces your hydronium ions, it simply means that salt was acidic. Now, how do you get to know if you have got a salt of NH4 plus and Cl minus, and you would have obviously two ions, NH4 plus and your Cl minus. Your Cl minus would be ions from a strong acid, hydrochloric acid, and your NH4 plus would be ions from ammonia. So it is these ions from a weak base that would undergo salt hydrolysis. When they undergo salt hydrolysis, you'll have NH4 plus H2O, and you'll get as a product. Now remember, that NH4 plus will not be accepting any proton. Instead, it would be donating. Now you'll have NH3 plus your H3O plus. And because of that hydronium ion, we say that salt, which is your ammonium chloride, was an acidic salt. So it's always advised that you are able to identify your acids and your base from the word go. Now, obviously, we look at our reaction as a neutralization, where we are just doing titration. When you are doing titration, we've talked on the choice of your indicators, that you have got pH range that you look at, a pH range of a basic, a pH range of a neutral, a pH range of an acidic. Now, obviously, a strong acid and a strong base, you use bromethymol blue because that will give you a neutral solution. A strong acid and a weak base, you would use your methyl orange because you'll get a solution that is more acidic. And a weak acid and a strong base, you use phenolphthalein because that will give you a solution that is more basic. And remember, when we talk about titration, there is always going to be salt and water that is produced. Two is that there is always going to be a standard solution that is prepared. When you are preparing a standard solution, remember we talk about a solution of a known concentration. Let's get to the last two questions, which are under your electrochemistry. First question that we look at with electrochemistry is a galvanic cell. Back in the days, we used to even call it a voltaic cell. Now, remember, when we look at electrochemistry, we look at energy conversion that takes place in the cell. Now, if you look at your galvanic cell, the energy conversion that is taking place there, it is from chemical energy to electrical energy. Three is that when you look at your galvanic cell, you look at a redox reaction that is always going to be spontaneous. And that reaction of a galvanic cell will always be an exothermic reaction. Now remember, when we talk about the exothermic reaction, we talk about a reaction that gives out heat to the surroundings. We always make use of a zinc copper cell to unpack what happens to a galvanic cell. How do you differentiate a galvanic cell from electrolytic cell? A galvanic cell will always have a salt bridge. You need to know the role of a salt bridge. What does the salt bridge does in that? Now remember, if we look at our zinc copper cell, both electrodes are your active electrodes. Now remember that we look at the flow of electrons. An anode electrode in a galvanic cell will always be negative. A cathode electrode in a galvanic cell will always be positive. And the flow of electrons is always going to be from anode to your cathode. An anode electrode is an electrode that is found under your oxidation reaction. And you define the oxidation reaction by two. One, you define it in terms of electron transfer, that your oxidation reaction is loss of electrons. Two, you define your oxidation reaction in terms of oxidation number, that when you look at your zinc, it's undergoing oxidation. Its oxidation number is 0. You look at your zinc ions, its oxidation number, it is a 2+. Now from 0 to 2, there's an increase. Obviously, when you are defining oxidation in terms of oxidation number, you say oxidation is an increase in oxidation number. We look at your cathode electrode. The cathode electrode, that's where gain of electron is taking place. As they move from anode, they are moving towards your cathode. Now, at your cathode, that's where reduction is taking place. In terms of electron transfer, reduction is gain of electrons. And if reduction is gain of electrons, we define it in terms of oxidation number. You can see that your copper ions have got a 2 plus, and your copper solid has got an oxidation number of 0. From a positive 2 to a 0, it simply means there is a decrease in oxidation. 3, you need to be able to write a cell reaction or a net cell reaction. When you write a net cell reaction, you have got both your oxidation and your reduction. Now remember, we always need to balance your electrons. For this instance, electrons are balanced, so it's easy for us to write the net cell. 3 is that you need to be able to write a cell notation. When you are writing a cell notation, you need to identify a reducing agent. You need to identify an oxidized space, an oxidizing agent, and a reduced space. Now you start with what is happening on oxidation, because a reducing agent is a substance that undergoes oxidation. Now for this scenario, our reducing agent is zinc. And our oxidizing agent is a substance that undergoes reduction, or is a substance that gains electrons. So oxidizing agent here becomes your copper ions. Now, your oxidized space, obviously, it would be your zinc ions. Your reduced space, it would be your copper as a solid. Now, you need to always know that in a cell notation, the first substance or the first agent has to be a solid electrode. And the last one, it has to be a solid electrode. If from the half cell you do not have solids, you need an inert electrode, which is a platinum. Another thing that you need to know from a cell notation, there are lines. The first set of lines is the double lines that you would have separating an oxidized space from an oxidizing agent. It actually separates the oxidation from reduction. That double line is a salt bridge that we have. It separates the two electrolytes. You have got a single line in each and every reaction. One, between a reducing agent and an oxidized space, there's a single line. Between an oxidizing agent and your reduced space, there's a single line. That becomes a phase separator. Now, if it happens that an oxidizing agent and a reduced space are in the same phase, you differentiate them by a comma, not a phase separator. Learners, you always need to know that you have to calculate a cell notation. E naught cell, you don't have to abbreviate E cathode and anode. So your E naught cell has to be equal to E naught cathode minus E naught anode as it is written from the formula sheet. Or you say your E naught cell is equal to your E naught reduction minus your E naught oxidation. Or you talk about your E naught cell being equal to your E naught oxidizing agent minus your E naught reducing agent. Now, whenever you have got the two half cells, remember, the one that has got a smaller potential energy, if you look at the standard reduction tables, it will always be the one that is undergoing oxidation, which is taking place at your anode. And the half reaction that has got a larger reduction potential will be what will be undergoing a reduction half reaction, which is what will be taking place at your cathode. Now, you need to also be able to differentiate or relate the different strength of the reducing and oxidizing agent. You need to be able to identify an oxidizing agent or a reducing agent. You need to be able to differentiate a weaker oxidizing agent or a stronger oxidizing agent. And you state actions that will take place, which space will be reduced or which space will be oxidized. And obviously, what space will it be reduced to? Your last question. you look at an electrolytic cell. Different types of electrolytic cells that we look at, you need to understand all of them because you do not know which electrolytic cell you will come across. Your first one, you look at your electrolysis of sodium chloride. When you look at electrolysis of sodium chloride, remember, we are using inactive electrodes. Inactive electrodes mean your inert electrodes, which is your either platinum or your carbon electrodes. Now, when you look at your electrolysis of your concentrated sodium chloride, the electrolyte here will always be your sodium chloride. Two is that when you look at that electrolytic cell, how do we differentiate electrolytic cell from a galvanic cell? There's always going to be a source of energy, which is either a cell or a battery. Connected to terminals. A positive terminal will always be connected to a positive electrode. Now, in electrolytic cell, a positive electrode is an anode electrode, and a negative electrode is a cathode electrode. The flow of electrons still flows on the same direction from a positive, from your anode electrode to your cathode electrode. Now, in this scenario, it's flowing from a positive electrode to a negative electrode. Now, when you look at inside your electrolyte, your sodium ions are attracted towards negative because they're positive. Your chlorine ions are attracted towards your positive electrode because they are negative, but your water is attracted between the two. Your chlorine ions will be what is undergoing oxidation. And if you look at your water, because it is a stronger oxidizing agent than your sodium ions, your water will then be what is undergoing reduction, not sodium ions. And that is it with an electrolysis of your sodium chloride. Reaction number 2 that takes place in your electrolytic cells is your electroplating. Electroplating, you will always have the plated object at your cathode because that's what you are plating, that's what you are beautifying. And you will have your metal that you are plating an object with at your anode electrode. Now, we know already in an electrolytic cell that an anode electrode is positive and a cathode electrode is negative. But it does not change the fact that we know that a electrode, a anode, it's on your oxidation reaction. Your electrode, a cathode, it is on your reduction reaction. Now, if you are plating an object with silver, a silver metal will be your anode electrode. And the object that you are plating with, it should be what you have as your cathode electrode. Now remember, if you are coating with silver, an electrolyte must be an electrolyte that has got silver ions. Now, as you are doing your reaction, you would notice that you are producing silver ions as there's loss of electrons. On the other side, you are using up your silver ions as you are plating that object. So the solution will always be the same because the rate at which you are producing your silver ions is the same rate at which you are using up your silver ions. 2 is that this is an active electrode, electrode in your electroplating. If they are active electrode, it simply means if you are plating cathode with the metal at your anode, the metal at your anode, its mass will decrease, while the metal at your, or the object at your cathode, its mass will increase as you are coating or as you are electroplating it. The last 2 sets of your electrolytic cells, it is your purification of copper. When we talk about purification of copper, both electrodes will be copper electrodes. But now, you need to know that the other one will be the pure copper electrode. The other one will be your impure copper electrode. The one that will be your impure copper will be the one that will have its mass decreasing. And we know that the one that has got a mass that decreases is your anode electrode. So your anode electrode will be the impure metal, while your cathode electrode will be your pure metal. So as this reaction is taking place, the electrode that is your impure, it will corrode. As it corrodes, the impurity will stay there at the bottom, and the purity of it will then be attached to the pure electrode, or to the pure metal. Are we all together? So the mass of your anode electrode will be decreasing, because this is your active electrodes. The mass of your anode electrode will be decreasing, while the mass of your cathode electrode will be increasing. And what gets to be deposited there, or what gets to increase the mass of that cathode electrode, is the pure copper that is being removed from that impure. Now, a reaction that is taking place at oxidation, your copper is losing electrons to give us your copper ions and 2 electrons. At reduction, your copper ions are reacting with electrons to give us a copper solid. So you need to know that. Now, remember that that is the reaction that is taking place. So you should be able to write your oxidation and your reduction, and write the overall net for the purification of metals. And the last one, which we make use of your inert electrodes, it is your decomposition of copper chloride. Unfortunately, a decomposition of copper chloride, it is an electrolytic cell that we have covered in grade 8. When you are doing a decomposition of copper chloride, as a product, you should be getting E atoms Z2, which is your copper and your chlorine. Unfortunately, chlorine, we know it to be a diatomic compound, or a diatomic molecule, which it will be Cl2, which is a gas. Now, during the decomposition of your copper chloride, in solution here too, we know the electrolyte, it must have your copper chloride. The copper chloride that is there in solution, copper ions will be attracted towards the negative electrode, which is your cathode electrode, and your negative negative ions will be attracted towards the anode electrode, which is positive. And as it is attracted towards negative electrode, your positive electrode, your chlorine ions will lose electrons. And as they lose electrons, there is going to be a chlorine gas that is formed. So you'll find around your anode electrode, that's where loss of electrons is, there is going to be gas bubbles. At your cathode electrode, where the gain of electron is, your copper ions will be reacting with those electrons to give us a copper solid. So that electrode there will be covered with a substance that is of bronze. For grade 8, we talk about it being reddish brown. That's what will happen at that electrode. So it's an inactive electrode, because you need to have your inert, which are your carbon electrodes. Your carbon electrodes are inactive. They're not part of that, so they are not going to have the mass that is decreasing, or they're not going to have the mass that is increasing. That is it for paper 2. Now you need to remember, in this last part of electrolytic, not all of these 4 electrolytic cells that we have talked about are going to be part of the examination. There's only going to be one. But when you need to know all of them, unfortunately. You need to divide your time, because we are writing a 3-hour paper, and that 3-hour paper has got a multiple choice question of 20 marks. Divide your time, and good luck for examination. We have come to an end of our lesson. You can leave your questions on the comments. Do not forget to leave the name of your school, so we give shout outs. Please share, recommend, and subscribe to our YouTube channel. Thank you for watching. See you on our next lesson.